Good morning, everybody. I am so excited to introduce and to host Dr. Reva Kay Williams here with us today. We had wanted, Guru Jagat for some time had wanted to have an actual astrophysicist, cosmologist, somebody who understands the stars from a mathematical point of view on to Aquarian Women's Leadership Society during an eclipse cycle to talk about, the universe from a mathematic and scientific perspective. And so I went on the hunt for it. Dr. Reva Kay Williams is very unique in multiple ways, being the first in so many different areas. First, Black female theoretical astrophysicist in the United States, first woman to solve a very large theoretical problem of a kind and work with this certain kind of, you'll have to explain it, Reva Kay, because you told me, and I also was reading it in your bio about one of these things that you really broke the other glass ceiling that you broke in these sort of theoretical models. But she's also really significant in that she is someone who came to the study of cosmology and exocosmology through, or exogalactic cosmology, which you can talk more about, through a deep, profound connection with the divine, with God, and so a merger of sort of, not even a merger, but just a yes, a both and, which is yes, there's math, there's science, and then at the end, when it's like, well, how did it all begin, and where does it end, and why is it expanding at an accelerated rate? You have this space of the profound devotional heart. And so it was just such an amazing fit, and I'm so thrilled to host you here today. So thank you, Reva Kay.
Well, thank you so much for having me. I feel really honored, and I thank you so much. I get a chance to once again tell my story. Now, many years ago, I decided that when I decided I wanted to be an astrophysicist, I believed that God, the main reason was that I believed that God created the universe, and I wanted to find out how he did it scientifically so that I can tell people. So I'm here today to tell my story and to reveal to you that God of infinite intelligence and knowledge created the universe. So let me begin. So you will find out in this talk that it's just like it said in the Bible. In the beginning, God created the heavens and the earth. And God said, let there be light. Now that's an important statement. Let there be light. This happened about 13.7 billion years ago. So first, I will walk you through some of the fascinating celestial objects in the universe. And then I will end with our present epoch. Now, I have to begin my talk by saying something about Einstein and Isaac Newton. These were the two scientists that made me fall in love with physics. When I was first introduced to these scientists' laws and theories of gravity and motion, I fell in love with the physics. And that basically sealed my faith in my becoming an astrophysicist, one that studies the physics of the universe. Now, it's something that before I found out that these scientists were two of the greatest scientists in the world, I fell in love with their physics. And then later, after studying their laws and finding more about physics, or increasing my knowledge of physics, then I found out that they both worked on gravity and the laws of motion. Now, what really caught my interest was that when I studied their laws, they seemed to relate to life. For example, Newton's first three laws of motion says, the first law says, once an object is set in motion or at rest, it will continue in that motion in a straight line at a constant velocity or at rest unless acted upon by some outside force. His second law says that force is equal to mass times acceleration. Now, our mass is the amount of matter in an object. And so when you go to the first law, the law of inertia, I'm sure you all have heard someone or come across it in your lifetime where people say, you know, I just can't get started. Or you may hear someone say, well, you know, I keep doing the same thing over and over, and it's just like, I just can't really get out of this place. They don't realize that the law of inertia is working against them. And so in order to get out of that law or to overcome that law of inertia, you have to have a force. And that force is mass time acceleration. Acceleration means a change, a rate of change. So you have to do something in life, maybe go back to school, maybe learn a new skill. So these laws, they're really simple and we follow them every day, but we don't realize that these are the laws of nature. And then the third law is for every action, there's an equal and opposite reaction. Now that's biblical. You know, you reap what you sow, what goes around comes around. And so actually we experience these laws every day. You know, when something happens, you know, well, what you put into it, you'll get out of it. And sometimes, you know, that works in a negative way because if someone do something, you know, that's really unjust, then it's going to come back to them. And then his law of gravity, which is an attraction, it says that the gravitational force is equal to that G is the Isaac Newton gravitational constant. So it's a mass, say, of one person times the mass of another. And it's divided by the distance squared. So in other words, this is saying that the closer someone is, the closer you all are. It could be an organization, it could be a couple, the greater the force you're going to have. And then later I'm going to relate that force and tell you that faith is also a force, but it's a spiritual force. I'm sorry. Now Einstein's laws, I found after studying Isaac Newton's, because when I would in physics courses, it seems like every time the professor would get to the chapter on general relativity, he would skip it. And so finally, when I went to Northwestern, that's when I finally got a chance to study general relativity. And it simply says that, to put it in a nutshell, his equations describes motion in a gravitational field. It says that clocks run slower in a gravitational field. The second item we have studied, it has been proven over and over again. And then to relate it to life, I'm sure that you've run across it or maybe you experience it yourself, that when a person is really progressing in life, you know, say two people graduated from high school at the same time, and they were, and one person just went out and just did things and improved his life and took care of his family, had a nice job, worked hard on their skill. And then the other person, say the same age, and they just sit around and really didn't do anything in life. And then you see them, it's like the person that really was doing something accelerating in life, they appear to look younger. And so that law has been proven. And so I'm sure that you have seen that in your lifetime. The third law says that gravity is equivalent to acceleration. Now, the way that Einstein would explain that, he said, if, say, a person was in an elevator, and if the elevator started going up, this person, and it went up at the same acceleration of gravity, this person will be, he would be attached to the floor just as if he was in a gravitational field. And then the fourth one that his equations described, it says that it shows that objects it shows that space-time is curved around a massive body. And here I show, let me get my laser printer. So usually when they talk about gravity, they use the analogy of a rubber sheet. And so here would be the mass. And if you have a rubber sheet and you put a object, something that weighs a lot, then it's going to make the sheet sink down. And this is what Einstein describes as gravity, because if the mass of gravity is here and it sinks down, then anything that you put on that sheet is going to be accelerated toward this massive object. And these would be the trapped orbits, say for instance, the trapped orbits in our solar system of the planets. So next so let me get started. First, I will talk about the solar system. So in this journey, I'm going to start with our solar system, and then I'm going to start with I'm going to be looking back in time, and I will talk about our galaxy, and then I would venture on out to extragalactic astronomy. Now, I'm sorry. Okay, so let me just begin with our solar system. Okay, our Earth, we belong to a group of planets, a group of 8 planets. It used to be 9, but Pluto was downgraded to a minor planet. And so I will talk about each one. I will briefly talk about them. So let me begin with Mercury. Mercury is a planet. It looks very much like our moon. It's the closest planet to the sun. It doesn't have an atmosphere because of its distance, its short distance from the sun. Mercury doesn't have an atmosphere, and so it has extreme temperatures. The daytime temperature is about 700 degrees Fahrenheit, and then it goes down to like 100. It goes down to 100 Kelvin. So I will talk, when I talk about temperatures, I would talk about Fahrenheit because that's the one that we're most familiar with. And then I would talk about absolute zero temperature, which is in Kelvin. So you'll hear me talk about them, but the numbers, you will know that they are either very high or very low. The next planet, a distance from the next planet, which is the closest, the second closest planet to the sun, is Venus. Venus, sometimes they say that it's the Earth's twin, but the conditions on Venus and the surface of Venus, they are very different from our sun. Venus has a large amount of carbon dioxide in its atmosphere. Its atmosphere is made up about 90% of carbon dioxide. Venus undergoes what we call a greenhouse effect, where the clouds keep the temperature in. And so the surface of Venus has a temperature of about 900 Kelvin, which is about 800 Fahrenheit. The cloud covering of Venus is very heavy. It's crushing. So we couldn't survive on Venus. We couldn't survive. And once the Russians, they sent a probe to Venus, and it was crushed after about a couple of minutes, but it did take some pictures of it. This picture, so this is the cloud covering. This one is a computer simulation of the data that was taken from one of the probes. And so Venus has a lot of volcanic activities on it. And then there's our Earth. Earth has an atmosphere made up of nitrogen and oxygen. And so I won't talk much about the Earth, so we'll just pass on. Okay, Mars, we've sent probes to Mars, the rover, and Mars has a very thin atmosphere of carbon dioxide, and it undergoes oxidation on it, which is like a rust. It has polar caps, which you can see here, like our Earth. And in the past, we believed that Mars once had water, running liquid water. Now it doesn't. It has frozen. We know that it has frozen carbon dioxide. And our next adventure, space adventure, is to reach Mars. and of course, go back to the moon. Next planet out, and this is the largest planet in our solar system, is Jupiter. Jupiter, it has a sort of liquid fluid-like surface. Jupiter was almost a star, but it did not have enough mass. And so Jupiter, it has very light density. And again, it's the largest planet in our solar system. Then there's Saturn. Saturn has an elaborate set of rings. These rings are made out of ice particles and rocks. Saturn is unique. Well, it has a surface like Jupiter, but it's unique because the density of Saturn is lighter than water. So what that means is that, say for example, something came in and flooded our solar system, Saturn would float. So just to keep that in mind, we should be trying to make it to Saturn if that ever happens. Okay, then there's Uranus, and that Uranus is a beautiful blue planet. It has a thin ring system. Its surface and composition is similar to Jupiter, which is made up of hydrogen and helium. And and also what's unique about Uranus is that it has where it orbits around the sun in a plane like the other planets, but its rotation axis or axis relative to the plane is almost I think it's like 98 degrees. It's almost 98 degrees. So Saturn basically, Uranus basically sits on its side. So that's what's unique about it. And the theory or hypothesis that maybe an asteroid or something came in that was large and knocked it off its planar orbit. And then there's Neptune. Neptune is a beautiful planet also, and it has the composition similar to Jupiter and Saturn. And it has a system of rings. Then there's Pluto. Now Pluto, well, it was once a planet, one of the major planets, but it always had these very different features. It was more like a ice, some kind of ice object. And then after our observations, we discovered that there were more objects out there like Pluto. So we downgraded Pluto to a dwarf planet. Now, these are pictures of comets. So this is what we believe that that Pluto, this is the family that we believe that Pluto belongs to. And these are comets, and they're outside, they orbit outside our solar system. And some of these comets have been perturbed out of their normal orbits, and they have these elliptical orbits, highly elliptical orbits, where they come in and make their appearance in the neighborhood of the sun, for example, like Halley's Comet. And then you see these two tails, one's a gas tail and one's a particle tail. And the ones that's made up of the particles that's the tail that's bent toward the sun because of gravity. So now next we want to talk about the sun. Our sun has a lifetime of 10 billion years. And the sun's age now is approximately 5 billion years old. This is a diagram of, I'm gonna just elapse this for a minute. So these are pictures or images of the sun taken in different light. This one is taken by an infrared telescope. This is an optical telescope. So the sun really has a white color. And then this is the sun taken in the ultraviolet, which is at higher energies. And then this is the sun in X-ray. which is higher than the energy of an electromagnetic ultraviolet radiation or photon. And no one can say anything, or no one can not realize the fact that the total eclipse of the sun is a spectacular event. When I first started studying astronomy, they were having a they were having a paper writing contest. And so this one person in my physics course, I was just beginning, I told him I was going to enter into it. And he said, well, why don't you talk about black holes? And so I really didn't know anything of black holes. So I went to the library and I got all of these books on astronomy. And so when I started reading about the solar eclipse, something just came and said to me, this is how it's going to be when black and white people finally come together. And if you've ever seen a total solar eclipse, you see how it's like the white sun, and then the black moon, it comes, and once the black moon has aligned with the sun, then you see this beautiful iron corona. And I said, then something just said, like, this is the way that our relationships would be once black and white people finally come together and realize that we all obey the same laws of God. So now let's journey out. Our sun is one of an estimate of 150 million other stars in our galaxy. Our sun, it orbits about the center of the Milky Way galaxy. And in the center of the Milky Way galaxy, now we realize that a black hole exists there. In fact, the Hubble telescope observations in 1994 revealed the existence of black holes, and also that most galaxies have a black hole at its center. This is a picture of a galaxy similar to our Milky Way galaxy. And I think on the other picture, the other diagram, you can see it better. But this is the center of our galaxy, and we have a bar in the center of our galaxy. Some galaxies have bars, some do not, and we believe that that's due to some sort of instability. So here, now you can see the bar in our galaxy, and then it has these elaborate spiral arms. This isn't that clear, but this is the budge, and these are globular clusters that are spherically distributed about the core of the galaxy. And then this is the disk. And then these are, well, I can't read that, so I'll just go to the other side. So when we observe the Milky Way galaxy, or the Milky Way, what we call the Milky Way, from Earth, this is what we observe, because we can't go outside our galaxy. And then here, where it's bright, this is Sagittarius A, this is the constellation, and this is where our black hole at the center of our galaxy is located. Now, our sun is a star. We found that stars, they are born, they live, and they die. This is a picture, this is a nebula, or nebulae. And this is what we call a nursery of newly forming stars. And so in this molecular cloud, newly born stars are embedded in here. And then this is another one, and you can see that these are newly forming stars. So stars, they are born, and then when a star is born, that's when its nuclear reactions are taking place at its core, where it is converting hydrogen into helium. Our sun is say a middle-aged star. Once a star takes and exalts the hydrogen at its core. A star has 3 ways to die. If the star's mass is, say, from 1 to 4 times our sun's mass, then when it exhausts its available energy at its core, it begins to burn, I'll say burn, hydrogen into helium in the outer shell, in the outer part of the core. Then it expands, the outer shell expands, and we call this a red giant. So once the star has exhausted its available hydrogen into helium, then it starts to collapse under gravity. Again, if the star's mass is from 1 to 4 times our sun's mass, it will collapse until finally the electrons that orbit outside the atoms, they put up a pressure and they halt the collapse. The final form of this evolved star would be a white dwarf. A white dwarf is about the size of the Earth. However, as it shrinks under the gravitational force, it becomes very, very dense. And so a teaspoon of a white dwarf would weigh about 2 tons. Now, when it first starts to collapse under gravity, gravitational energy is released. And so after the gravitational energy is released, then the star begins, well, at one time it was hot and then it begins to cool. Now, the substance of this star is crystalline carbon. That's a diamond-like substance. So in our universe, we have diamonds as big as the Earth floating around in the sky. So in other words, we have diamonds in the sky as big as the Earth. So I'm just going through some of the fascinating properties and objects in our universe. And the importance of this is that the universe is like a giant, organized, intelligent environment where, take for instance, you all remember the space shuttle. You can remember how much effort and intelligence that we had to put into the space shuttle to make it work the way that we designed it to. So with the universe, and as I continue to tell you about the objects, it's like something so intelligent created this universe that we have to get our PhDs, we have to go through all of this education just to try to figure out some of these properties of these objects in the universe. So this is saying that we had to have an intelligent designer to create this universe. And I have found that that designer is God. So what you all are looking at, this is when a star like the sun, when it turns into before it turns into a white dwarf, it takes and releases a large amount of this energy. And these are some of the diagrams. These are called planetary nebula that are released from these low mass stars like our sun. And then this is another, some more images of it. So again, there are 3 ways in which a star could die. If the star has a mass, say, from 5 to 10 times, excuse me, our sun's mass, when it undergo these final evolutionary phases, when it begins to collapse after it has exhausted its available energy at its core, it's violently. And so when it starts to collapse under gravity, electrons around the atom can't halt this collapse. And so it collapses until the neutrons in the atom, inside the atom, they halt the collapse. And this halt we call it the Pauli exclusion principle, where the electrons or they call the fermions, the neutrons, they refuse to have the same energy in the same state as another one. So either the spin has to be up or down. And then once that happens, and then you have to go to another energy level of the atom. So the neutrons put up this pressure and they halt the collapse. The final form of this core is a neutron star. But before the neutron star forms, when it starts to violently collapse under gravity, then the ejection of the matter from the surface is violent, and we call these supernova explosions. And what you're looking at, this is an artist's conception of it, and how they're saying here that when the star explodes under a supernova explosion, we thought that it would blow away all of this matter, but we find out that it doesn't. And so I would say that this matter, if it turns into a black hole, and that's the one I'm going to talk about, then this matter could be eventually accreted into the black hole. So now let me say something about the third way that a star can die. So once a star, if it has a mass, say greater than 10 times the solar mass, 10 times our sun's mass, when it starts to collapse under gravity, the electrons cannot halt the collapse. They can't put up enough pressure, neither the neutrons. And so the star continues to collapse until the gravitational field becomes so strong that light cannot escape. And then this is the formation of a black hole. And these are diagrams of images of supernova explosions. So these are very violent explosions. So I kind of just, I just went to, start talking about the black hole, but I want to say something more about the neutron star. The neutron star, when the collapse is halted by the neutrons, this star has a size about the size of a city, say Chicago. What's unique about these stars is that the angular momentum is conserved as the star is contracting or collapsing under gravity. And so it spins faster and faster. When the star forms to a neutron star, when the star evolves to a neutron star, it rotates from 1/100 from 1/10 to 100 seconds on its axis. So now just think of the power that's in a neutron star for something to rotate that fast on its axis and be the size of, say, a city. So that's a tremendous amount of energy. And so how we know that what's taking place, the characteristics of a neutron star is that they have a very large magnetic field, about 1 trillion times the magnetic field of our sun and the earth. And so if the rotation axis here, if it has the magnetic field axis would be here, if it's inclined to the rotational axis, and these are magnetic field lines. Then if you have an observer, say out here, when this star rotates, the energy that's along the poles, which comes out in the form of jets because the particles are interacting with the magnetic field. When it passes the observer out here, then it gives out a pulse as it goes around, and then it comes back, and we call these pulsars. So this is actually an observation of a pulsar, and you can see that this is the neutron star, and these jets are emanating from the core, and this is because of the magnetic field and the particles interacting with the magnetic field. This is another diagram which I explained how the physics of the pulsar. Now, I want to say more about astrophysical black holes. Black holes are one of the most fascinating objects in our universe. They have a tremendous storehouse of energy. It was not until the 1990s that we began to understand the physics of a black hole. And my work from my dissertation of 1991 And my publication of my paper in Physical Review Journal in 1995, which is based on the black hole physics of my dissertation, in which I extracted energy from the black hole using the Penrose mechanism. Well, that work contributed significantly to our understanding of black holes. In 1994, the Hubble telescope, as I mentioned earlier, strongly suggests that black holes indeed exist in nature. When I first began working on black holes, they have not been confirmed. In other words, their existence has not been confirmed. Then in 2001, it was suggested that it showed us direct evidence of energy being extracted from a rotating black hole. I was very excited about this because it was confirming my model. But unfortunately, when the paper came out, they mentioned the Penrose mechanism, but they didn't mention my work, my model. In other words, they mentioned my work and my model, but they didn't mention me. Black holes have masses ranging from 3 times our sun's mass to up to 1 billion times our sun's mass. And so the stars, the black holes that are have masses equivalent to our sun, we call these microquasars. And they are a scaled down duplication of the supermassive black holes. The supermassive black holes are found in quasars and in galaxies. Black holes are believed to power the most energetic objects in the universe, such as mysterious quasars and gamma ray bursts. So now we talked about the solar system, and then we ventured out to our sun. Well, our solar system, the sun is part of the solar system, but we ventured out to the Milky Way galaxy, and that our sun is one of 150 billion other stars in our galaxy. And now we are going to venture out to talk about extragalactic astronomy, as well as supermassive black holes, and then the black holes in our galaxy. So when I talk about the supermassive black holes, remember the microquasars, or the stellar size black holes, are basically a scaled down form of the supermassive black holes. So let me just go. So this is what we observe. These objects, quasars and other active galactic nuclei, we observe a source here that's emitting a tremendous amount of energy. And for a long time, we suspected that they were black holes, but now we know that they are black holes. These black holes are generating a tremendous amount of energy in the form of jets. And these jets are emanated from the polar region, and they go out to, say, kiloparsecs. And then this is a picture of a quasar. And notice the jet extending out to very large distances. This is the counterjet. The reason why you don't see the other part of the counterjet is because this radiation is Doppler boosted to higher radiation. This is the jet that's coming towards us. I almost pointed in the direction of the observer. And then this one is blue red shifted or Doppler boosted in the other direction. And so that's the reason why you see the asymmetry. This is an artist's conception of an active galactic nuclei. And so these are the jets. And my work, it describes how these jets are formed or generated. This is another picture of a active galactic nuclei. And here you can only see the one-sided jet, and that's because of Doppler boosting. This is the artist's conception of a black hole. In my work, I use frame dragging to increase the energy of the particles. So as the particles fall in, and we call this, when they start falling in toward the black hole, they encounter a region we call the ergosphere. Inside the ergosphere, anything that falls into the ergosphere must rotate in the direction that the black hole is rotating. So particles are in the ergosphere orbiting at these very high energy orbits because of the black hole. The rotation of the black hole is dragging them around. Once the particles are in here, then a particle from outside, which we call the accretion disk, a particle can fall in and scatter off of one of these highly energetic particles and escape back outside the ergosphere to infinity, which is us, with the energy that these highly energetic particles had. Now, these particles with the very high energy, they were destined to fall into the black hole had it not been a process like the Penrose process to take this energy back out. And that's how energy is extracted from the black hole. And when the energy, when the particles are scattered, they escape along these jets that extend out to kiloparsec or megaparsecs, or and megaparsecs. Now, this is the artist's conception of what we observe. In my model, the particles escape in these vortical-like orbits, concentric the polar axis. And because these are electromagnetic or particles that have charge, then they create a magnetic field along the polar axis, and that's what we observe. And this is the accretion disk that accretes matter into the fourth event horizon, destined to fall into the black hole. Now, this is a diagram of, or an image of the event horizon of a black hole. These were taken by the Event Horizon Telescope. And I'm sure some of you all have seen this in the literature or in the news. And so here, what we are observing, this is the shadow of a black hole. So objects that are part of the accretion disk, they are accreted into what we call they are accreted toward the photon orbit. And so what we're observing light from the photon orbit, but it's on the other side of the black hole. And so the light that's on the other side of the black hole is gravitationally lensed to, so when the light comes up from behind, gravity from the black hole bends the light, and this is what we are observing. So this is light from the photon orbit. Now, in my work, I did scattering at the photon orbit, which had never been done. And the particles that I got from the scattering were electron-positron pairs. So electrons with the positive charge and electrons with a negative charge. And so these electrons were pair produced at the photon orbit. And so the light that we are seeing is light that's radiated in the radio. So when these electrons interact with that magnetic field that I showed you, that intrinsic magnetic field, they give off synchrotron radiation. And this radiation is synchrotron radiation that's is radiated in the radio of the electromagnetic spectrum. So basically my work can describe what we're observing. This next diagram, this is a diagram of an image, the same image, but here we included polarization. Now polarization, the way they measure it is proportional to the electron density and the magnetic field. So it's a combination of both. So for my model, these would be the particles in these vortical-like orbits that are escaping concentric to the polar axis. And they are interacting with their intrinsic magnetic field. And this is what's producing the synchrotron radiation. And I want to say that the competing model is the Blanford-Denied type model. However, that model The main problem is that it cannot generate these high energy electron positron pairs near the event horizon. So only, and what I call the Penrose Williams model can do that. And the reason why I made the distinction was because after I had shown that my model worked in details, then the proponents of the Blanchard type model, they started publishing work saying that Blanchard type model was doing what I had shown in detail my model to do. And that would have been fine if they had just published it, but they didn't reference my work, and that was the problem. And so they attributed all of my work to the Blanchard type model, was not, which was a falsehood. Okay, so now you know about the event horizon the event horizon of the black hole and our observations. So now we're going to venture out even more. And when we look out in time, when we look out in the universe, the further out we look, or the furthest distance we look, we are looking back in time. And so what that means is that, well, let me explain that. So because light is a constant and its velocity is 186,000 miles per second, when we look out at an object, it takes light a certain amount of time to reach us. So if we look out at an object that's, say, 1 billion light years away, then it took 1 billion years for that light to get to us. And so when we look at those objects, we're looking at them the way they looked 1 billion years ago. So when I say that we're journeying out to the edge of the universe, we're basically journeying back in time. Now, our galaxy, now remember, our sun is one of 150 billion other stars like our sun in the galaxy. Our Milky Way galaxy is one of 150 billion other galaxies besides our Milky Way galaxy. So now you can see the vastness of the universe. This is a picture of a cluster of galaxies. Each one of these elongated surfaces or dots, that's a galaxy. And they're elongated because of gravitational lensing. And gravitational lensing simply says that because space-time is warped, whenever an object comes from a distance and passes through the strong gravitational field of another object, then the light is bent. And so these circles, they call them Einstein rings, where the light is being bent around the large gravitational well produced by other objects and galaxies in the vicinity as the light is passing by those galaxies. This is another picture of galaxies, and here you can see some of the galaxies, but all of these little dots, those are galaxies, like our Milky Way galaxy. And then this is another image. You see the galaxies. So now we've gone out to the edge of the universe. So now we're going to look at it like that's like the beginning of the universe. Now our physical laws can take us back to time, t equal to 10 to the minus 43 seconds. So that means that you have t is equal to, and we have what, 42 zeros. That's how far we can go back in time. Our physics break down after that. But so we can go all the way almost back to t equal to 0, but we cannot go back to t equal to 0. And so I remember taking a astrophysics course in when I was an undergraduate. Now remember, I started studying astronomy because I believed that God created the universe, and I wanted to find out how He did it. And so when it was an astrophysics course, and it was only like 3 people in the course, and we had the class inside the professor's office. So we talked about quasars, which are the most distant objects in the universe, and he said, I asked him, well, what is it after that? And he said, once we get out to the quasars, or the furthest obviously in the universe, then that's when religion takes over. So that was a big step for me, because I came home, because I believe that, well, I had found a professor that actually said that religion takes over when we get so far out or so far back in time. And so this is what our physics tell us, that approximately 15 billion years ago, there was a gigantic explosion of infinite energy, and it came from something that was so small that was smaller than an atom. It was so small, it appeared that it came from nowhere. And so okay, and when we go back, the reason why it appears that, like, we said was smaller than an atom, because, as I said, it appeared that it came from nowhere. And it was infinite energy, infinite density, more energy than we can ever imagine or measure. And so something caused this a tremendous amount of energy to explode and start expanding in all directions. Now, we know that, okay, so now we call this the Big Bang. So how do we know the Big Bang actually occurred? Number one, we have tested it. First of all, we know that energy can neither be created or destroyed. It can only change its form. So that energy had to come from somewhere. And the organization of our universe says that it has to be an intelligent being to actually start that. Because again, like with the space shuttle, it's like we had to do something to make that space shuttle take off. We had to provide the energy, the necessary thrust to make it take off. Something had to provide the energy for the universe to begin. And as it expanded, it cooled, and eventually our galaxies and our solar system formed. So when this tremendous amount of energy was released, it was in the form of photons. Photons are light particles. So it was just like God said. In the beginning, God created the universe, and God said, let there be light, and there was light, and there was light at the beginning of the universe in the form of photons. So this is the diagram that we always show of the cosmic evolution. So in the beginning, we start with the Big Bang. Once the Big Bang occurred, then you had quantum fluctuation. So quantum mechanics and gravitation, the forces were combined. And so now you probably heard of quantum gravity, where we're trying to combine these forces so that we can understand what goes on inside a black hole, and also what took place immediately following the Big Bang. Now, immediately following the Big Bang, after like t to the minus 32 seconds, the universe went under what we call an inflation. So at one time, the four forces of nature were linked in this quantum fluctuation. And the four forces are gravitational force, electromagnetic force around the atom, the weak force, which governs radioactive decay, and the nuclear force inside the atom. So when these forces took and separated as the universe was cooling, then it caused a tremendous amount of energy was released, and it caused the universe to inflate. Okay, so that's the inflation. And here, they call this the afterglow pattern. This is the last scattering of a photon. So the last scattering, it means that the photons and the electrons, because of the high temperature, they were just scattering each other. Then eventually, as the universe cooled, then hydrogen atoms were able to form. And so the electron became part of the atom. And so the electron, that was the last scattering of the photon. And this is the pattern that we see when we measure the 3-degree background radiation, which is the radiation that was left over from the Big Bang. Now, so the second proof that we have is that this radiation was predicted to be present and permeating over the universe by George Gamow. And then in I think it was like 1964. I know that they won the Nobel Prize in 1978. So Robert Penzia, and I mean Robert Penzia and Robert Wilson, they discovered this background radiation, and they were Bell Laboratory physicists, and they discovered this radiation. And then after the hydrogen atom formed, we went through a dark period where there were no stars and just the hydrogen. And then eventually, as the universe cooled more and more, stars were able to form from hydrogen. And this is the first. This is considered as the first time that the stars formed. And then eventually, as the universe cooled and galaxies formed, planets, and then eventually we find ourselves here. Now, as the universe was expanding and cooling, we knew that gravity should eventually start the universe to slow down. So we observed, I think it was like it was in the early 90s. We observed these stars that we knew the process of them. And so we were able to determine their distances. These are like supernova 1A stars. But then what we found is that instead of slowing down, the expansion was speeding up. It was accelerating. And so now we don't know what's causing this acceleration. And so we just say that it's dark energy. But the acceleration is being caused by something. And people have different theories about or hypotheses about what's causing it. And I did a paper, and I put it on the archives, that perhaps the universe is rotating. And I say that because when I study black holes, and the way that the jets are generated is because the rotation has associated with it what we call the gravitomagnetic field, which is the gravitational analog of a magnetic field. And so as the black hole is dragging space-time around, this gravitomagnetic field is produced because you're dragging inertia frames around. And this gravitomagnetic field, it has a repulsive component, which is how the jets are generated in black hole. So my hypothesis is that if the universe is expanding, then it should have associated with it a gravitomagnetic field. And this gravitomagnetic field, because of the rotation, could be causing the universe to accelerate. So that's my take on it. So now we are here today. Our observations have led us to things that we don't understand, which one time we thought we understood about the universe. And those are the things that we understand is the dark energy, which comprises about 70% of the matter in the universe. And then there's the dark matter, which causes objects to form under gravitational forces. It caused the formation of galaxies, and it's so many other things like the rotation period, like our galaxy. We thought that the rotation should slow down as you go further and further from the center. However, the rotation is basically, it's not going down. And so we know that matter is out there, but this matter, it doesn't interact with the particles that we know. It doesn't interact electromagnetically. It only interacts with gravity. So about 30% of the matter is dark matter. So we only know very little about the composition of our universe. Now, let me get to the part. So how did God create the universe? in the Bible, it says that faith is the substance of things hoped for, the evidence of things not seen. So that means that faith is the evidence. Now think about this. Of faith is the evidence of things hoped for. I mean, faith is the substance of things hoped for, the evidence of things not seen. And so it appears that, like God said, it takes faith to please God. And then it's in the Bible, whatsoever we said and not down our heart, but believe those things which we said shall come to pass. We shall have whatsoever we said. It says that it only takes a mustard seed of faith to move mountains. So it appears that with the faith of God and the faith in his word, that he actually spoke into existence when he said, let there be light. And there was light, and the universe began. Now, I'm going to close. So that's my proof that God created the universe. When you look at the universe and all the beautiful objects and the organization of the universe, then it had to be an intelligent being. And I say that that being was God, and that he spoke it into existence with his powerful words. Now, as I close, it reminds me of an article that I read also when I was a senior at Northwestern University, and it was in Scientific America. And it said, basically, once physicists and astronomers and astrophysicists have done all of their calculations to take us back to the beginning of the universe, when they got there, the theologians were there waiting for them. Thank you very much. That's the end of my talk.
Dr. Reva Kay, that was so amazing and special and fantastic, and illuminating and fascinating. And the Penrose mechanism was the term for the mathematical model that I was trying to remember, where I knew that you had solved some really large problem, theoretical problem that I couldn't recall. So thank you for, again, sharing that, and also sharing just the academic struggle of what it is to be a woman, and not just any woman, an African-American woman. And it's like, they don't credit your work.
Yeah.
It's like they credit you, they talk about your work, and then it's like, well, who started this? Oh, it's just, it's always been there. It's like, no.
Yeah.
I did it. I
Right.
did that. It's just, trying to look me over. But blessed by your ability to just continue to bring your brightness and your brilliance. And in this time where we are working out, it's like the credit where credit is due, and the relevance of our leaders, our female leaders, our female Black leaders.